Okay, this is the limit marathon video. In this video, we're going to solve about 70 limit problems. And so what I've done is I've taken about 70 limit problems of all levels of difficulty. So mixed in are easy, intermediate, and advanced limit problems. And then mixed in are all of the different types of limit problems. So limits as x approaches a finite number a, with both two-sided and one-sided limits, with the limit function being all types of different functions. And so where the limit could exist and be equal to L, or maybe the limit doesn't exist and is D and E, or maybe the limit doesn't exist because it's an infinite limit. So the limit is equal to plus or minus infinity. Also mixed in are some limits at infinity and some infinite limits at infinity. And so what I've done is I've taken all of these problems, thrown them into a hat, and just picked problems at random from the hat. So we might start with the hardest problem first, or we might start with an infinite limit at infinity first. The order of these problems is completely random. Okay, so let's get started. Okay, the limit as n approaches infinity of minus n over n squared plus n plus 1. So here we've got a limit at infinity, right? The input variable is approaching plus or minus infinity of a rational function, right? This is a ratio of polynomials. So we know there's a standard procedure to solve any limit at infinity of a rational function. What you do is you just divide the numerator and denominator by the variable to the power that's the order of the denominator polynomial. So in this case, that would be squared. So we're going to say that what we're doing is we're manipulating the limit function to put it into a different form. Because if we plug in infinity, we get infinity here, and then infinity squared plus infinity plus 1 is infinity. You have infinity over infinity. Really, this is minus infinity over infinity, but any kind of infinity over infinity is an indeterminate form. And what we do with indeterminate forms to solve limits with indeterminate forms, the main technique is L'Hopital's rule, which we're going to learn about in chapter 4. And we're really going to go into detail on not just L'Hopital's rule, but indeterminate forms of limits in chapter 4. But at the moment, if we come across an indeterminate form of a limit, the way we solve it is by manipulating the limit function, putting it into a different form that doesn't result in an indeterminate form. And so with the way we do this with rational functions is, again, we divide the numerator and denominator by in this case, n, the variable, so n to the power of the order of the denominator. So you've got minus, we're multiplying by 1 over n squared over 1 over n squared. Okay, so you've got, all right, so now when we plug in infinity, you have 1 over infinity goes to 0. 1 over infinity goes to 0. 1 over infinity squared goes to 0. 1 plus 0, the denominator goes to 1. So this entire limit goes to minus 0 divided by 1, or just 0. Okay, now if we take a look at the graph of this function, we can see as n goes to infinity, the function is approaching 0. We have a horizontal asymptote at y is equal to 0. The horizontal line y is equal to 0. Now the function is approaching 0 from below. That's something else you could note, but exactly how the output approaches the limit value doesn't matter in terms of what the limit is equal to. Okay, the limit as x approaches infinity of x over cosine of 1 over x. So, okay, we can plug in infinity, even though technically that's not something that's mathematically correct to plug in infinity, but I find it useful to look at this as, so cosine of 1 over infinity, and just keep in mind that these infinities are not the same number. Infinity is not a specific number. You just have cosine of 1 over some arbitrarily large number. So huge number, bigger and bigger and bigger number, like 100 quintillion. Well, that's going to be something very close to 0. So what is cosine? Like 1 over infinity is approaching 0. So what is cosine of 0? That's 1. So this is approaching 1. Cosine of 1 over x, as x gets bigger and bigger and bigger and bigger and bigger, cosine of 1 over x is getting closer and closer and closer and closer to 1. Okay, so now you've got infinity in the numerator, so it's really some huge number, 100 quintillion, 500 quintillion. divided by something that's very close to 1, positive 1. Well, that's just going to be whatever the number in the numerator is, right? Just infinity. So this is equal to infinity. So if we look at the graph of x over cosine of 1 over x, we should see as you go down the x-axis, the function is just ballooning to larger and larger positive values. And there you go. So when you get around 0, you have all kinds of activity going on because you're dealing with this oscillating cosine function, right? And then also x is getting, when it's getting close to 0, x is getting bigger. So there's a lot going on around 0, but with this limit, we're not concerned with that, right? We're not concerned with what's happening when x is around 0. Not at all. We're looking at what's going on out here. It's just as x gets bigger in the positive direction, the function output gets bigger in the positive direction. Okay, another limit at infinity. So the limit as r approaches infinity of minus e to the r over r squared. So, okay, e to the infinity, and then, so e to the arbitrarily large number is just going to be an arbitrarily large number. Infinity squared is just going to be another arbitrarily large number. So you've got minus infinity over infinity. That's indeterminate. Because we can't say, you might think, oh, well, infinity divided by infinity, well, that's just going to be another arbitrarily large number. 500 quintillion divided by 200 billion is just another huge number. Yeah, in that case, that's true, but what if these two infinities are similar? What if the rate at which e to the r is increasing is very similar to the rate at which r squared is increasing as the inputs increase? Well, this could be close to 1, right? You can't make a statement about any kind of infinity over infinity. So, okay, now we could use L'Hopital's rule here. In fact, if we had covered L'Hopital's rule would be perfect for this. But at the moment, we're just focusing on fundamental limit techniques. So what we can do is we can analyze e to the x in comparison to x squared, or e to the r in this case, with just the e to the independent variable with respect to the independent variable squared, and see, okay, is it the case that e to the r rises much faster than r squared? So, okay, if we've got e to the x and then x squared. So let's plug in x is equal to 5 here. Okay, now with x squared, let's plug in 5. Right, well, look, there you go. That's just when the input has gone up to 5. Imagine if we're going to infinity, right? We could take this and plug in 100. Now let's plug in 100. Yeah, so this exponential here, e to the r, rises significantly faster than r squared. So this is going to balloon to a large number in magnitude, but is it positive or negative infinity? Well, this just goes to positive infinity, and this goes to positive infinity, but with the negative out front, you're going to end up with the whole limit going to negative infinity. So if we look at a plot of this function, there you go. As x gets bigger, I mean, we're only up to like 9 here, and look how fast this is e to the r over r squared. I mean, this is going to negative infinity quick. So again, as the input gets bigger and bigger in positive magnitude, the output's going to get bigger and bigger and bigger in negative magnitude. So this is an infinite limit at infinity, right? Let's see, here is an infinite limit at infinity, and here's a limit at infinity in which the limit existed. So this is a horizontal asymptote problem. Okay, the limit as x approaches 3 from the right we've got a rational function here, a ratio of polynomials. Okay, so we're not going to be using the technique of dividing the numerator and denominator by x squared here because this isn't a limit at infinity, right? That technique only applies with a limit at infinity of a rational function. So now this is the first limit that we're working that's not a limit at infinity. So it's the limit as x approaches a finite value. And so if you're not dealing with a limit at infinity, the first step is to always check to see if the limit function is continuous at the limit point. Because if it is, then you just plug the limit point into the function, and whatever it evaluates to, that's what the limit is equal to, right? That's the direct substitution property. The limit as x approaches a of a function in which the function is continuous at a is just equal to f of a. And what's nice about the direct substitution property is that the majority of the types of functions that we're most familiar with from algebra and trigonometry are continuous everywhere in their domains. Rational functions, polynomials, roots, any kind of root, an even or an odd root, logarithms, all the trig functions. As long as the function exists at a certain input, then the function is continuous at that input. So we're going to start by let's just plug in 3. Now, the fact that this is a one-sided limit, don't worry about that because, as we've talked about, the mechanics and whole theory of one-sided limits is exactly the same as two-sided limits. And in fact, one-sided limits are easier to deal with because you only have to consider one side of the limit point. So, okay, you plug in 3, you get 2 in the numerator, then 9 minus 12. Okay, so no, this function is not continuous at x is equal to 3. All right, so what do we do next? Well, okay, since we know that x is equal to 3 is a discontinuity. If it's not a point of continuity, then it must be a discontinuity. So anywhere that a function doesn't exist is going to be a discontinuity. Now, it doesn't mean that if a function exists at a point that then you're 100% dealing with a point of continuity. That's not always the case, but it is always the case that if the function doesn't exist, then that is a discontinuity. So the question is, are we dealing with, like, what type of discontinuity are we dealing with? Is it a removable discontinuity? Is it a jump discontinuity? Is it an infinite discontinuity? Or is it perhaps an oscillating discontinuity? Well, we know that if we're ever dealing with a ratio and a division by 0, that there's a good chance that we're dealing with, assuming we're approaching a finite value, single value, there's a good chance we're dealing with a vertical asymptote. Now, that's not 100% always the case, but here that is going to be the case because plugging in 3, this is approaching 2 divided by 0. If we plugged in 3 and we saw that this was approaching like a 0 divided by 0, then that most likely wouldn't be a vertical asymptote. It still potentially could be. It's not like an indeterminate form of a 0 divided by 0 has no chance of being a vertical asymptote. But what we saw is that with rational functions, a 0 divided by 0 case was when, so if we would factor this, and one of the factors was an x minus 1, and the x minus 1's canceled, and we were doing a limit as x approached 1, then that wouldn't be a vertical asymptote. That would be a hole in the graph, right? But here, as x approaches 3, the numerator is going to approaching some non-zero value, and the denominator is approaching 0. So this is going to be you're taking a finite value and dividing it by a number that's closer and closer and closer and closer to 0. So you're going to be ballooning. The output's going to be ballooning to a large value in magnitude. Now, so okay, we know this is going to be an infinite limit. This is going to be equal to plus or minus infinity. But the question is, which one? Is it plus or minus? So let's see. Let's see if we can factor the denominator to make this a little bit easier. So 3, 1. Okay, so there we go. We've got, and then the x minus 1's cancel, so that there still is a hole in this graph at x is equal to 1, but we're not concerned with that, right? Because we're analyzing as x approaches 3 from the right. Okay, so as x approaches 3 from the right, you're going to have like 3.0001 minus 3, 3.000 1,000 zeros 1 minus 3. So this is always going to be positive in the denominator. 1 is always positive, so 1 divided by a tiny positive number is positive infinity, but then we've got this negative out front. So this is going to be negative infinity. And if we look at the graph, so as x approaches 3 from the positive direction, the function is going to negative infinity. And you've got this vertical asymptote. Anytime you have any kind of infinite limit associated with the limit as x approaches a finite value, you know you're dealing with a vertical asymptote at x is equal to that value. So x is equal to 3 is a vertical asymptote. Okay, the limit as s approaches minus 6 and we have another rational function. Now, again, this is not a limit at infinity, so we're not going to be dividing the numerator and denominator by s squared. But, okay, if we plugging in minus 6, we see that the numerator is 0. And so now in this case, if the denominator also goes to 0, then we've got a 0 divided by 0 case, which is going to result in you're going to get a graph with a hole in it, right? Because if we, so factoring the denominator, we've got s plus 6, s plus 2, and then s plus 6. And so that the s plus 6 is canceled. Now, but just note, though, it's not like any 0 over 0 form of a limit means you're always going to have just a hole in the graph. Well, no, it depends. It depends on, for the specific limit, how fast is the numerator approaching 0 and how fast is the denominator approaching 0. A 0 over 0 form could be anything. It could go to infinity. It could approach whatever. But in this case, for the case of these rational functions, the numerator and denominator are approaching 0 at the same rate because you have the same factor that's going to 0. You have 0, and this is approaching 0, and this is approaching 2, but these two zeros are the same 0. So, which is why as the function itself approaches the input of minus 6, the function doesn't do anything different. It doesn't balloon to positive infinity. It doesn't do anything different than what it would normally be doing. But at s is equal to minus 6, since 0 divided by 0 doesn't exist, there's a hole in the graph. So, okay, what you've got is, this comes out to, you have 1 over s. Okay, so what all this function is it's minus 1 over s plus 2, but you just put a hole in the graph at s is equal to minus 6. Okay, and so what's the limit going to be equal to? Well, we know that since we just have a continuous curve, and then when we get to some point, we put a hole at a single point and then just continue on with the curve. Well, the limit is just what the function would be equal to if there's no hole here. So we just plug in minus 6 into here. So minus 6 plus 2 minus 1 over, so 1/4. This limit is equal to 1/4. And so, yes, there is a vertical asymptote in this function at s is equal to minus 2, because it was s plus 6 over s plus 2 times s plus 6. So at s is equal to minus 2, the denominator is going to 0 and the numerator is going to positive 4. But we're not concerned with what the function is doing at s is equal to minus 2 for this limit. We're concerned with what the function is doing around s is equal to minus 6. So there's the hole at s is equal to minus 6. And as s approaches minus 6 from either side, the function is approaching 1/4. Okay, the limit as x approaches minus 5 pi over 6 from the right of minus secant of 2x. So we know that secant is the reciprocal of cosine. So this is okay. Now plugging in minus 5 pi over 6 for x, we get, so cosine of minus 5 pi over 3. So you've got, go radian mode, minus 5. Okay, so now we can just take the reciprocal of that. The function is continuous at the limit point. So 2, but with the minus sign out front. So if you plug in minus 5 pi over 6, you get minus 2. Trig functions are continuous everywhere in their domains. All the functions that we're familiar with from algebra and trigonometry are continuous everywhere in their domains. And we plug this in and we got a value. So that the limit is equal to minus 2. If we take a look at the graph, so secant, if you recall, does have vertical asymptotes. There are parts of secant to where the function is not going to exist because you're going to be dividing by 0. But in this case, we're not at an asymptote. So minus 5 pi over 6 is about minus 2.62. So here's minus 3. Here's minus 2.5. So we're right around here. So There you go, minus 2. It's just continuous here. Okay, the limit as c approaches 4 of the principal square root of 2c plus 4. Let's just plug in 4 and see what we get. Roots are continuous everywhere as long as you're in the domain. So 4 times 2 is 8. So we're going to end up with an argument that's greater than or equal to 0. So there you go. All right, 4 times 3. So you have 2 root 3. Right, so a root is continuous everywhere in its domain. So 4 is in the domain of this root. So there you go. It's continuous. The limit is just equal to what the function evaluates to. Okay, the limit as w approaches 22 of 5. 5 is just a constant function. It's the horizontal line at y is equal to 5. That's continuous everywhere in its domain, but its domain is all real numbers. The output of this function is always 5. It doesn't matter what the input is. This is equal to 5. So here's y is equal to 5. If we come down to 22, but it means the same graph everywhere, but here's f of 22. So the function is always just approaching 5. Okay, once again, we've got a root here, a third root, but roots are continuous everywhere in their domains. So let's just plug in 1. So 2 times 1 is 1. You have the third root of minus 1, but that's okay. For an odd root, the principal third root of minus 1 is minus 1. But now we've got a minus out front, so 1. There you go. This is continuous everywhere, so just plug in 1. And you get, here's 1. It's approaching just whatever the function evaluates to at 1. Okay, we're back to another limit at infinity. Now you look at this and think, okay, yeah, we're going to divide by t to the power that's the order of the denominator. However, you have to be careful in this case because this is not a rational function. That rule only is bulletproof for rational functions, right? The expression in the numerator is not a polynomial. This is not a rational function. But we're still going to use that same technique where we're going to divide the numerator and denominator by t squared, but we still need to be careful in terms of how we deal with this root here. Now, this actually isn't going to be a problem in this case because t is approaching infinity, but it's really when you have a case where t is approaching negative infinity, where you'd have to be careful dividing something like this, the numerator and denominator by a t squared. And even actually in this case, even if t was going to negative infinity, it wouldn't even matter in this case either. It wouldn't get messed up because, okay, if let's go ahead and treat this like it's a rational function and divide the numerator and denominator by t squared. So you get, and see what happens. So, okay. Now, what we do here with the root is we're going to divide this by t squared in the form of the square root of t to the 4th. Now, the reason why in some cases you have to be careful for something like this, and this is really going to be when t is approaching, or the input is approaching negative infinity, is because, like, if you have if you had a squared, the principal square root of a squared, right? This is not equal to a. The reason why is because this is equal to the absolute value of a. It's not equal to a because if you just said it was equal to a, then you would be saying that this is equal to minus 5. That's not true. This is equal to positive 5. Now, in this case, it actually doesn't matter because if you had the principal square root of a to the 4th is actually just a squared. You don't need an absolute value because you're squaring this anyway. But you can see how for other problems, you have to be careful with how you would, if this was going to negative infinity, how you would write this expression here. So, okay. But just simplifying this, right? And I'm saying that it only matters if the input is going to negative infinity because, yeah, this is equal to a if a isn't negative. It's only an issue when the a is negative. But if a is negative and you're doing this, well, then it doesn't matter if a is negative because you're squaring it. You don't need the absolute value. Okay. So you've got, this is going to be 1 over t. Okay. Then 2. Okay, so now plugging in infinity, you have 2 over infinity goes to 0. The denominator goes to minus 1. Here, this goes to 0, so you have 1 over infinity cubed is 0. The square root of 0 is 0. Plus 1, this goes to 1. So 1 divided by minus 1 is minus 1. If we take a look at the graph, as the input t goes to infinity, it does look to be the case that you have a horizontal asymptote at minus 1. Okay, another limit at infinity. But this is a rational function, so we can just divide the numerator and denominator by the order of the denominator, by x to the power of the order of the denominator. So you have x squared divided by x squared, x. So this is, you have 1 plus, then, okay, so this goes to 0. The numerator goes to 0. The denominator goes to 1. So this limit goes to 0. And that's what we see. As x goes to negative infinity, the function approaches 0. There's a horizontal asymptote at y is equal to 0. Okay, here's another limit at infinity of a rational function, a ratio of polynomials. So we just divide by the order, t to the power, that's the order of the denominator. So 2t over t, t over t. Okay, so you've got minus 2, 1 plus. Okay, so the denominator 3 over infinity goes to 0. 1 plus 0 is 1. Numerator goes to 2. So this approaches minus 2 over 1. So you have a horizontal asymptote at t, or at y is equal to minus 2. And that's what we see here. 1, 2. As t goes to infinity, the function approaches minus 2. But it also looks to be the case that as t goes to negative infinity, you're also approaching, the function is also approaching minus 2. Okay, the limit as n approaches 3 pi over 4 of tangent to n. All right, well, we know tangent is continuous everywhere in its domain, so the first thing we can do is just plug in into this function. If the function exists, then whatever the function evaluates to at this n is the limit. All right, so tangent of 2 times 3 pi over 4 is 3 pi over 2. Okay, undefined. Okay, but now we know that, so tangent, the tangent function, is sine x over cosine x. And we know that there's no points where sine and cosine are 0 at the same time. Therefore, the only points where tangent doesn't exist, so the domain of tangent is not all real numbers like sine and cosine are. Sine and cosine have domains all real numbers. But tangent doesn't, and because there's certain points, input points, where cosine is equal to 0. But at those points, sine is not equal to 0, so there's never a 0 divided by 0 type case with tangent. It's always a finite number in the numerator, and then the denominator is going to 0. Cosine is going to 0. So tangent it's just continuous everywhere, but then there's vertical asymptotes mixed in. Anywhere where tangent is, you plug in an input value from negative infinity to infinity into tangent, and tangent doesn't exist, you know that's a vertical asymptote. So all we need to do is just, so we're at 3 pi over 4. Let's say it's here. We know this is a vertical asymptote of this tangent of 2n. We just need to see, is it the case that the function is ballooning, coming from either side of 3 pi over 4 to, from both sides to positive infinity or to negative infinity? In that case, we have an infinite limit here Otherwise, it's going to be just a D and E. So, okay, what we can do is take this, and so 3 pi over 2, that's 1.5. Let's do 1.445999 times pi. Okay, now let's do 1.500. Okay, so you can see that coming from below 3 pi over 4, tangent of 2n is doing this, and then coming from above, it's doing this. So this is just does not exist, D and E. And so this is 3 pi over 4. And there you go. The limit as n approaches 3 pi over 4 from the left is positive infinity, and from the right is negative infinity. So approaching 3 pi over 4 in general is just a D and E. Okay, the limit as t approaches 4 from the right of minus 1 over t squared minus 16. So plugging in 4, you get a 1 divided by 0 case. The numerator is approaching 1. The denominator is approaching 0. So this is going to be an infinite limit, or potentially a does not exist if perhaps this was a general limit approaching 4 from either side, and from one side the function was going to infinity and the other side negative infinity. But here with a one-sided limit, we are going to get an infinite limit. So if t is approaching 4 from the right, then that means you've got like 4.01 squared minus 16, 4.0001 squared minus 16. So this t squared is always something slightly greater than 16. So you're going to have 1 divided by a smaller and smaller and smaller, closer and closer to 0 positive number. So this is going to go to positive infinity, but with the negative out front, this entire limit goes to negative infinity. And that's what we see. Approaching 4 from the right side, the function is going to negative infinity. Okay, the limit as p approaches 2 from the left of the absolute value of p minus 2 over p minus 2. Well, what we do here is, with the absolute value, we want to analyze the domain portion of this function that we're considering. So we're only considering when the input is less than 2, right? Because we're strictly to the left of 2. So if p is always less than 2, then p minus 2 is always negative, no matter what. So we can simplify this absolute value. We can say that if p minus 2 is always negative, then we want to take the negative of p minus 2 so that we get a positive. So now we've got these p minus 2's cancel. This is approaching. So this limit is equal to minus 1. If we take a look at the graph, you see that as p approaches 2 from the left, the function is approaching minus 1. Okay, the limit as t approaches minus 4 of h of t, where h of t is this piecewise defined function. Okay, so the limit is approaching minus 4, which is the transition point of this piecewise function. And so what we need to do is we need to analyze what exactly this function is doing at the minus 4 transition point. Is t is equal to minus 4 a discontinuity? If it is it a jump discontinuity? Is it a removable discontinuity? Or maybe the function is continuous at minus 4. It could be continuous at minus 4 since the function is defined at t is equal to minus 4 based on this parabola here. This function is going to be continuous everywhere. So the domain of this function is all real numbers, right? Because you have a polynomial here, which are continuous everywhere. And then, but this function is also defined at this the transition point minus 4. So the domain of this function is all real numbers. And this function is continuous everywhere other than at minus 4 because you just have 2 polynomials. So the question is, well, what's the function doing at t is equal to minus 4? So let's plug in minus 4 into this parabola here first and see what we get. So minus 10 So minus 16 plus 40 minus 25 minus 16 plus 15 minus 1. Okay, now let's plug in minus 4 into this second polynomial. Okay, so you get minus 1 in both cases. That means this function is continuous at t is equal to minus 4. So there you go, the direct substitution property. If the limit function is continuous at the limit point, then the limit is just equal to the function evaluated at the limit point, h of minus 4. h of minus 4 is minus 1. Right, and so this function is continuous at minus 4, but it might not be smooth. So we've got, if this is minus 4, this is minus 1. So here's that transition point. Well, you've got this downward-facing parabola. Maybe it's something like this, and then this positively sloped line, right? So it's just like not a smooth point here, but it's still continuous. You could draw what this function through t is equal to minus 4 without picking up your pen off the page. And yeah, there you go. There's the graph. It's continuous here, approaching from either side. Function is approaching minus 1. Okay, the limit as x approaches minus 7 from the left of 4 times the absolute value of minus x minus 7 over minus x minus 7. So, okay, with an absolute value, we want to analyze if we're strictly considering x values that make it so that the argument inside of the absolute value is always positive or always negative. So if we're coming from the left side of minus 7, so that's like minus 7.5, minus 7.2, minus 8. So, okay, if you've got minus and then minus 8, minus 7, so that's 8 minus 7, positive 1. So, yeah, minus x minus 7. As long as x is less than minus 7, you're going to get a positive number inside of this absolute value here. So we can simplify the absolute value. We can say that we just remove the absolute value, right? Minus x minus 7. So now these cancel, and we're left with... Okay, so just a constant function. The limit as x approaches minus 7 from the left of 4 is just equal to 4. We take a look at the graph. So as you're approaching minus 7 from the left, the function is approaching 4. Okay, the limit as t approaches minus infinity of t over sine of 3t. So plugging in negative infinity, we get, and then 3 times negative infinity is just negative infinity. So, okay, what is sine of negative infinity approaching? If you keep inputting a larger and larger and larger negative value in magnitude into sine, what's the output doing? Right, sine of negative 100,000, negative 100 million, negative 100 trillion, negative 100 quintillion. What is sine, the sine function doing? Well, we know sine and cosine just oscillate forever and ever between minus 1 and 1. Yeah, I mean, we have this multiplier, this 3 here, but that's just going to change the period. Cut the period down by 3, a factor of 3. This function is still just going to be oscillating forever and ever between minus 1 and 1. So this is going to be approaching, it's going to be just oscillating from minus 1 to 1. And so that's an issue, because what that means is that with a minus infinity up here, you're going to be flip-flopping between a positive and a negative value. Perhaps if this was the absolute value of sine of 3t, in which case we would strictly have negative outputs, then maybe that limit it still wouldn't probably exist, because you would be oscillating between dividing by a tiny number to dividing by 1, but maybe that would result in an infinite limit. Maybe the limit would approach plus or minus infinity, but here, this limit is just going to be a D and E in general, because you're oscillating between, you're going from a value in the denominator that has magnitude of 1, that's getting really close to 0, goes all the way to 0. So actually, you're going to have some values where you are dividing by 0, but then you're also flip-flopping between positive and negative values. So D and E. If we take a look at the graph, yeah, so as x goes to negative infinity, the graph is flip-flopping. And the magnitude is constantly changing. Okay, the limit as x approaches 1 of minus x over x minus 3. So it looks like we can just plug 1 into this function. This is a rational function, continuous everywhere in its domain, so 1/2. If we take a look at the graph, there is a vertical asymptote at x is equal to 3, but we're concerned with what the function is doing at x is equal to 1. It's continuous at x is equal to 1. Okay, the limit as c approaches minus 3 of c over 1 over c plus 3 minus 1 over 3. All right, so as c approaches minus 3 of minus 3 plus 3 approaches 0, 1 divided by a number approaching 0 is infinity. And actually, that's not true, because if c is approaching minus 3 in general, then, yeah, if c is approaching minus 3 from the left, then 1 over c plus 3 is approaching minus infinity. If c is approaching minus 3 from the right, then 1 over c plus 3 is approaching positive infinity. So let's see. From the left, you're approaching positive infinity, or negative infinity. From the right, you're approaching positive infinity. So negative infinity minus 1/3 is negative infinity. Positive infinity minus 1/3 is positive infinity. So you have a negative infinity and a positive infinity. Then c is approaching minus 3. Okay. But now minus 3 divided by some number that's bigger and bigger and bigger and bigger and bigger in magnitude, positive or negative, is going to approach 0. The sign's not going to matter in this case because we're approaching 0, right? Minus 3 divided by minus 100 quintillion is something very close to 0 from above 0. Minus 3 divided by positive 100 quintillion is still something very close to 0 but below 0. So this is equal to 0. And as c approaches minus 3, that's what we see. And actually, this looks like it's a removable discontinuity. So let's see, where's that coming from? If we simplify this, if we multiply the numerator and denominator by 3 times c plus 3, we get, so 3 minus, and then c plus 3, and then 3c times c plus 3. So you've got minus c down here, and so these cancel, and you're left with minus 3 times c plus 3. So minus 3c minus 9. So there you go. This simplifies to a line, but you still have a hole at c is equal to minus 3. This is the line minus 3c minus 9. Again, with a hole at c is equal to minus 3. Okay, the limit as x approaches infinity of 2x squared plus 1 squared over x minus 1 squared times x squared plus x. All right, so this is a limit at infinity of a rational function. So we just want to divide the numerator and denominator by the x to the power that's the order of the denominator. So in that case, what we're going to get is you have an order 2 here and an order 2 here. So this is going to be an order 4 polynomial. So we want to divide by x to the 4th. Divide the numerator and denominator by x to the 4th. So it might be easier to just go ahead and expand this out. So you've got, let's see, x squared minus 2x plus 1, then x squared plus x, then 4x to the 4th plus 2x squared plus 2x squared. Okay. So you got x to the fourth plus x cubed minus 2x cubed minus 2x squared plus x squared plus x. So you've got x to the fourth, then minus x cubed minus x squared plus x. Okay, there you go. So now dividing the numerator and denominator by x to the fourth, you get okay, so 4 plus 4 over x squared plus, okay, now infinity, plugging in infinity, all of this goes to 0, all of this goes to 0, so this limit goes to 4. You have a horizontal asymptote at y is equal to 4. Right, there you go. Okay, the limit as r approaches 1 from the right of 5 times the absolute value of r minus 1 over r minus 1. So if r is always above 1, then r minus 1 is always positive. So we can simplify the absolute value by just removing it. So these cancel, and you're left with, okay, the limit as r approaches 1 from the right of 5 is just 5. Because approaching 5 from above 5, here's the function. The function is approaching 5. Okay, the limit as b approaches 0 from the left of minus secant b. So secant is 1 over cosine. All right, now, perhaps if we plug in 0, then we're going to get an output here. And this function is going to be continuous. Secant is continuous everywhere in its domain. So, yeah, cosine of 0 is 1. Minus 1 over 1 is minus 1, so there you go. Secant does have vertical asymptotes because cosine can be 0. The output of cosine can be 0, but that's going to be at like pi and 2 pi. At 0, cosine is equal to 1. So that's why here secant, when the input is equal to 0, it's just continuous here. Approaches minus 1. Okay, the limit as t approaches 3 of the square root of t plus 1 minus 2 all over t minus 3. So as t approaches 3, we see the denominator goes to 0, which makes us think that this is perhaps a vertical asymptote problem. But as t approaches 3, the numerator goes to, so 3 plus 1 is 4, square root of 4 is 2, 2 minus 2 is 0. The numerator also goes to 0. So we have an indeterminate form, the 0 over 0 indeterminate form. Now again, we're going to talk about indeterminate forms in a lot more detail in Chapter 4. So at the moment, to solve indeterminate forms, what we do is we need to manipulate the limit function to put it into a different form that's not indeterminate. And so now a really useful tip that you want to keep in mind when going through school in algebra, trigonometry, and calculus, really any undergraduate math, is for any problem you're working on that involves a two-term expression like this, which is you have one of the terms is a square root term, and then it's plus or minus another term that could be a square root term, but it could be a non-square root term like this. Then there's a high likelihood that the conjugate of that expression is going to be involved in solving the problem. So, for example, here, the next step is we want to multiply this by 1 in the form of the conjugate of the numerator. So square root of t plus 1 plus 2 over the square root of t plus 1 plus 2. And the reason why we want to do this is because this is going to greatly simplify the numerator and then just overall put this expression into a new form. And the reason why this works is because if you've got a two-term expression being multiplied by its conjugate, then what you're left with is you get a squared and then minus ab plus ab, the two middle terms subtract out, and then minus b squared. So the two middle terms subtract out, but then furthermore, you're squaring a and b, which gets rid of the roots. So even if both terms have a square root, both of the roots get eliminated. Now just keep in mind, though, it doesn't work this way with an expression like this that involves any root. It's like a third root, fourth root, whatever. This only works with square roots because, so like if we were multiplying the fourth root of x cubed by the fourth root of x squared plus 1, well, the roots aren't going to be eliminated in this case because 1/4 plus 1/4 is 1/2. So the result of this multiplication is this, right? It's only with a t plus 1 to the 1/2 times t plus 1 to the 1/2. The 1/2 plus 1/2 gives 1. So the root goes away. So, okay, what we're left with is, so the square root of t plus 1 times the square root of t plus 1 is just t plus 1. And then minus 2 times positive 2 is minus 4. So we're just left with t minus 3. And then in the denominator, we've got so these cancel, and we're left with, okay, so now plugging in 3, we get, so 3 plus 1 is 4, square root of 4 is 2, 2 plus 2 is 4, so we get 1/4, which is what this limit is equal to, because all we've done is just take the limit function and put it into a different form. And so what this means is that this function, the graph of this function, is this exact graph, except with a hole in this graph at t is equal to 3. Because even though these two functions are equivalent, you can't divide by 3 here. So you can't divide by 3 here either, because we just took this and put it into this form. And so anytime with a limit, if you have a hole in the graph, so a hole in the graph is just like this, right? The function might be defined here, it might not be. Here it's not defined, but here it is defined. Doesn't matter. And this is not a jump discontinuity, so a hole is not a jump discontinuity. This is not a hole. Only something like this is a hole. Then the limit as the input approaches a hole is just what the function would be equal to if it was defined at the hole. That's it. And again, this is completely independent of if the function is undefined at the hole or it is whatever. Regardless, the limit as the input of a function approaches a hole in the graph is just what the function would be equal to if it was defined at the hole. So all we do here is just say, okay, well, since these two graphs are exactly the same, except this graph has a hole in it at t is equal to 3, well, okay, then we just plug 3 into here, because that's what this would be equal to if it was defined at the hole at 3. And so there you go. There's the graph. There's the hole at t is equal to 3. So the limit as t approaches 3 of, so here's the function, right, with the hole in it, is just equal to what the function would be equal to if it was defined at the hole, which is 1/4. Okay, the limit as x approaches infinity of the square root of 9x squared plus x minus 3x. So, okay, plugging in infinity, we've got huge positive number squared is just another huge positive number times 9, just another huge positive number, plus that huge positive number, just a huge positive number. Take the square root of that. You get some arbitrarily large positive number. Minus 3 times arbitrarily large number is just another arbitrarily large number. So, okay, infinity minus infinity is an indeterminate form. We can't make any definitive statement about what it means to take an arbitrarily large number and subtract from that another arbitrarily large number. We could if this was a plus, because, okay, arbitrarily large positive number plus another arbitrarily large positive number must be another arbitrarily large positive number, right? But this Okay, you have 100 quintillion minus 550 billion. That's going to be an arbitrarily large number. Or you've got like 100 quintillion minus something very close to 100 quintillion. That's approaching 0. Or maybe it's approaching something like 100. Like, you have no idea. Okay, so again, right now, when we're dealing with an indeterminate form, we're going to learn a lot more about indeterminate forms in Chapter 4. But at the moment, what we do is we manipulate the limit function to put it into a different form that's not indeterminate. And so again, here we see that what we're dealing with in this problem, a two-term expression that involves a square root. The second term doesn't involve a square root, but it could as well. And so the vast majority of the time in undergraduate math, when you've got an expression like this, then solving the problem is going to involve the conjugate of this expression. So to put this expression into a different form, what we want to do is multiply by 1 in the form of the conjugate of this. So then plus 3x. Okay, what we're left with is, so you get 9x squared plus x, and then minus 9x squared in the numerator. So we're just left with x in the numerator and square root of 9x squared plus x plus 3x in the denominator. Okay, so now plugging in infinity, we're going to get infinity over infinity, which is still an indeterminate form, but this is an indeterminate form that we know how to work with. Because what we're going to do is we're going to divide the numerator and denominator by x to the power, that's the order of the terms in the denominator. So in this case, x to the first. Now with the root, we need to be careful, right? This isn't a rational function. We're dealing with a root here, but since x is going to positive infinity, this isn't going to be a problem. We're just going to divide this root term by x in the form of the square root of x squared, but we don't have to think about how this would be equal to the absolute value of x if x was negative. So, okay. All right, so this simplifies to, you get 9 over x plus 1. Okay, so as x goes to infinity, you have 9 over infinity goes to 0, plus 1 is 1, square root of 1 is 1, 1 plus 3 is 4, so the denominator goes to 4, so this limit goes to 1/4. So this limit is equal to 1/4. If we take a look at the graph, yeah, so as x goes to infinity, the function approaches the horizontal line, y is equal to 1/4. The limit as x approaches minus 2 of the floor function of x squared plus 2x minus 5. Okay, so I know personally when I was going through math, if I was ever dealing with a non-conventional function, so a function that wasn't something like a trig function, a rational function, logarithm, exponential, some kind of ratio, etc., then I always felt intimidated. But what I came to realize was that there's really nothing to be intimidated by at all, no matter what kind of function you're dealing with. So if you're dealing with a Heaviside function or some sort of error function, there's nothing to be intimidated about, assuming you understand the operation that's being applied to the function or whatever analysis is being applied to the function. Meaning, so in this case, we're performing a limit on this floor function. But we understand exactly how limits work, right? As far as the limit of a single variable function, so a function with a single real number input and a single real number output, we know pretty much everything there is to know about limits. We still have a little bit more to go through as far as going over specifically all the indeterminate forms and L'Hopital's rule, but other than that, we know everything. And so the reason why in the past I might get intimidated by a problem like this is because I think I would inherently assume that a problem like this is going to be something different that I've never seen before. But that's not going to be the case because if we think about it, so every single variable function whatsoever is going to have a graph. A single variable function with a single real number input and a single real number output has a graph in the XY plane. Because all of the potential inputs are contained on the real number line, right? The x-axis. So if an input is in the domain of the function, you just evaluate what the function is equal to and plot it on the y-axis. If it's not in the domain of the function, then you just don't have a graph at that x point. Okay, so no matter what the function is, no matter how unconventional it is, it's going to have a graph in the xy plane. And what you want to think about is that there's not going to be a feature of the graph of that function that we didn't talk about in these sections on limits and continuity. Because any potential point that you can input into the function on the x-axis, on the real number line, is either going to be a point of continuity or a point of discontinuity. One of the other. There's no third option in terms of continuity. All potential input points into a function are either continuous or they're not, which means they're discontinuous. They're points of discontinuity. So if the function is continuous at the limit point, well, we know what to do, right? Just plug the limit point into the function. Whatever the function evaluates to at that point is what the limit is equal to. But if the function isn't continuous at the limit point, which means it's a discontinuity, then we just need to figure out what kind of discontinuity it is. Whatever the discontinuity is, even for an unconventional function, is going to be either removable, jump, infinite, or oscillating. And we know exactly how to analyze a limit associated with any one of these discontinuities. So, okay, what we need to do here is we want to think about, so what is this function? How does the floor function work? Well, a floor function always rounds down. So if you input 6.9 into the floor function, then the output is 6. If you input 2.1 into the floor function, the output is 2. If you input minus 8.2, then it's going to round down to minus 9. So, okay, how does a floor function with a parabola as the input work? Well, okay, here's the graph of this entire function, which you could graph in Desmos. You can graph a floor function in Desmos. Okay, and so you can see that clearly there's jump discontinuities everywhere. But even with all of these jump discontinuities, what you want to think about is that it's still the case that the majority of input points into this function are points of continuity, right? Because each one of these lines is continuous everywhere away from the endpoints. So one of the first things that we would want to do when analyzing this limit is see, is the limit point on a jump? Or if it's not on a jump, then it's on a point of continuity. And so if it's on a point of continuity, then you just input the limit point into the floor function, evaluate the floor function, and that's what the limit is equal to. But even if it is on, even if this input is on one of these jumps, then we still have the answer to this limit. It's going to be DNE, because this is a general two-sided limit. At a jump discontinuity, a general two-sided limit always doesn't exist, because the limits coming from either side are different. That's why it's a jump discontinuity. Okay, and so then you might say, well, all right, the limit point is an integer. That's where all the jumps are associated with the floor function at the integers. You're jumping from one integer to another. So this is going to be D and E. Well, no, not necessarily, because this isn't the basic floor function, the floor function of x. This is the floor function of this parabola. So if we overlay the graph of this parabola onto the graph of the floor function here, so here's the parabola, the dashed line is the parabola x squared plus 2x minus 5, then what you can see is these jumps are occurring when the output of the parabola gets to the next integer value. But these x values, these input values for which the output of the parabola is an integer, aren't necessarily integers themselves. We can see here, when the output of the parabola is 1, this is not an integer. And then when the output of the parabola gets to 2 here, this also isn't an integer, the main input. This is about 1.83. And so the idea is when x is equal to this 1.65-ish, the output of the parabola is 1. And so there should be a closed circle here. And then as x increases towards 1.83, then you're always just, here's the output of the parabola, but you're always just rounding down to 1. But then once you get to this 1.83, when the output of the parabola equals 2, then you've got a jump to this next line here, to y is equal to 2. The horizontal line at y is equal to 2. So there should be an open circle here and a closed circle here. It's the same idea if we look in the negative region. So as the inputs into the floor function go from this x to this x, in which case the output of the parabola goes from -1 to -2, right? You can see -1 to -2. There's your integers. Well, this x is about -3.23. It's not an integer. And this x actually happens to be an integer. When x is equal to -3, the output of the parabola is -2. Okay, and so now you're still always rounding down. In the positive or negative region, you're always rounding down. But in the negative region, you're going to have the open circles on the left and the closed circles on the right. Because if the output is -1, then you're staying at -1. But when the output gets to -1.000001, then you round down to -2. But not when you're exactly at an output of -1. At an output of exactly -1, you stay at y is equal to -1. Okay, so that's how the floor function works. So you can see that the first thing we want to do is, let's just plug in -2 and see if the argument inside the floor function is an integer or not. If it's not, then just apply the floor function, round down, and that's what the limit is equal to. So, okay, -2 squared plus 2. So 4 minus 5. So, okay, x is equal to -2 does result in an integer. So here's x is equal to -2, and yeah, the output of the parabola is -5. So we know we're at a jump discontinuity, which means we know that the general two-sided limit means that this is going to be, does not exist. Because approaching 5 from the left and approaching 5 from the right are two different limit values. But we can still just take a look at this and see what would the one-sided limits be equal to. So, well, actually, that's easy. Coming from the left, the limit as x approaches -2 from the left would be -5, and from the right would be 6. It doesn't matter what the actual floor function is, if this is an open circle or this is a closed circle. It doesn't matter. But just to show you, so there would be a closed circle here and an open circle here. And then here's closed circle, here's open circle. So like in this entire region, the function is always rounding down to -6, except when the parabola output is equal to -5, then you stay on these lines, because in this region, you're either equal to -6, or the output of the parabola is equal to -6, or it's something between -5 and -6. So you always round down to -6 in this region. Okay, the limit as r approaches -3 of 3 over r squared minus 9. So plugging in -3 for r, the denominator is going to 0, but the numerator is 3. So this is a vertical asymptote. Now, is this a case of is this a D and E case, or is the function going to plus or minus infinity on both sides of 3? So, okay, as r approaches -3 from the left, this means that you've got, -3.01, -3.001, -3.0001 is being plugged in here. So in that case, you've always got some number that's just a little bit greater than 9 being subtracted from 9. So 3 divided by a tiny positive number that's close to 0 is positive infinity. And with the negative out front, you get negative infinity. Now, the limit as r approaches minus 3 from the right is, so you've got, so like minus 2.89, minus 2.899, minus 2.9995, minus 2.99999 into the function. So like something just below 3 squared is going to be something just below 9, which is going to result in a tiny negative number in the denominator. So 3 divided by a tiny negative number is negative infinity, times minus 1 is positive infinity. So in general, this limit does not exist. If we look at the function, yeah, minus 3 is a vertical asymptote, but the function is approaching negative infinity from one side and positive infinity from the other side. Okay, the limit as w approaches 7 of w minus 7 over w squared minus 12w plus 35. So, okay, the numerator is going to go to 0, and the denominator, if it doesn't go to 0, then this limit is equal to 0, but I'm assuming the denominator is going to go to 0 as well. So if we factor the denominator, we get w 7 times 5. 7 plus 5 is 12. So, yeah. So this simplifies to the limit as w approaches 7, and the w minus 7s are going to cancel, so we're going to get over 1. So this function is exactly equal to this function, except when w is equal to 7, there's a hole in this graph. So with a hole in the graph, we just figure out, okay, what would the function equal to if there wasn't that hole? We just plug in 7 here. So 7 minus 5 is 2. This is 1/2. And so as w approaches 7, the function approaches this hole. And at the hole, the function it would be equal to 1/2. Okay, the limit as s approaches minus 1 from the left of f of s, where f of s is this piecewise function with a transition point at minus 1. And then, but away from the transition point, you've got a polynomial and a constant function. So this function is going to be continuous everywhere and defined everywhere, and it's going to be defined at minus 1 as well, defined as 0. And so we might be able to just plug in minus 1 into the function. So f of minus 1 would be 0, but that just depends on if what the function is doing at minus 1. Is the function continuous? Is it a jump discontinuity, a removable discontinuity? So we need to analyze what the function is doing at minus 1. So let's plug in minus 1 into s minus 2. So s minus 2 at minus 1, you've got minus 1 minus 2 is equal to minus 3. And then at 0, at minus 1, this is equal to 0. So, okay, what we have is a jump discontinuity. When s is less than minus 1, the function is the line s minus 2. So s minus 2 has y-intercept minus 2 and then slope 1. So it's like that, right? So it would be starting here and just continuing down, but there's going to be an open circle here, and then when s is greater than or equal to minus 1, you just have the constant function. Y is equal to 0. So you have a jump discontinuity, right? So as s approaches minus 1 from the left, the function is approaching, what would the line s minus 2 be equal to at minus 1? It would be equal to minus 3. So this is equal to minus 3. And that's what we see, right? Coming from the left, function is approaching minus 3. Okay, the limit is w approaches minus pi over 4 of 2 cosecant of w. So we know that cosecant is the reciprocal of sine. Okay, so, I mean, it looks like we could just plug, this is just continuous at the limit point. So Let's just do cosecant of minus pi over 4. Yeah, so this function is just continuous at the limit point. So just plug in the limit point, minus 2 root 2. There's 2 cosecant of w, so minus pi over 4 is around minus 0.78. So here's minus 1. So right around here. Minus 2 root 2. Okay, the limit s approaches minus 7 from the right of h of s. And so we're looking at the transition point here. So what's happening at the transition point? Is this a discontinuity? If it's not, then this limit is going to be equal to just h of minus 7, which would be, so it's defined based on this function. You're just plugging in minus 7 here. If there is discontinuity, then we need to look and see what kind of discontinuity is it. So, okay, let's plug in minus 7 here. We get, so minus 7 squared minus 14 times minus 7 minus 49. So we've got 49 times minus 1, then plus 14 times 7, then minus 49. So this is equal to 0. Okay, now here we've got minus 7. Okay, so this is also equal to 0. So the function is continuous at minus 7. So just what is h of minus 7? That's just going to be 0. So this limit is equal to 0. So there you go. It's continuous. It doesn't necessarily have to be smooth, but smoothness doesn't come into play when it comes to evaluating limits. It's just that it's continuous. We can draw this without picking up our pen off the page. And so at s of minus 7, the function is equal to 0. Okay, limit as x approaches 0 from the right of f of x. Okay, so once again, let's just analyze what the function is doing at the limit point. So what is this function? What is this function equal to at the limit point? This is 2. What about this function? This is 9/2. So what we've got is a jump discontinuity. When x is less than 0, you've got some upward facing parabola. And then when x is greater than 0, you've got some line with a negative slope. So at 9/2, that's what? 2, 3, 4, like 4.5. When x is 0, you have the y-intercept is here, then with a negative slope. So, you know, something like that. And then here you've got this upward facing parabola. And then you would have an open circle here and a closed circle here. And so, okay, as x approaches 0 from above 0, the function is approaching this value, which is the 9/2. So this is equal to 9/2. There you go. So that's the parabola. It was at, yeah, I should have put it at, yeah, x is approaching 0, but it was, when x is equal to 0, this is equal to 2. So I should have put it here. And then the parabola, you don't actually get to see any of the dip in the parabola when you're this zoomed in. It's just like that. So the parabola might look like that in full. And so, yeah, there you go. Approaching 0 from the right. The limit is based on what would this function be equal to if it was defined at this point. And that's what this would be equal to at 0, at x is equal to 0. Okay, the limit as w approaches 0 of minus 4w over the absolute value of minus w. So for any problem in math, if you're ever dealing with an absolute value, the first thing you want to think about is, can I simplify that absolute value? Can I get rid of it? And the way you're going to get rid of it is because whatever the domain that you're considering, the domain of inputs, those inputs are such that the value of w is either going to always be positive or always be negative. And in that case, that's when you can simplify the absolute value. But here, it looks like we can't do that. We can't do that because we're considering w approaching 0 from both sides. Now, just because you have a two-sided limit doesn't mean that you can't simplify an absolute value. I mean, you could have an absolute value that looks something like this. But if the limit point you're looking at is over here, you could still simplify the absolute value, right? But here we do have the transition point of the absolute value, that kink point where it switches from positive to negative. That is the limit point. So what do? Well, okay, remember, one of the techniques that's easy to forget about, techniques for solving limits is, so if all else fails, then what you could do is you can analyze the two one-sided limits associated with a given limit separately. And that could give you some really useful information. Because if you can find, like, one-sided limits are easier to deal with than two-sided limits. So if you can find both of the one-sided limits, then okay, if both of those limits are the same, well, then the general limit is equal to that value. If both of those limits are different, then the general limit doesn't exist, right? So we can say, okay, what's the limit as x approaches 0 from the left of this minus 4w over the absolute value of minus w? Well, in this case, now w is always negative. So how can we simplify the absolute value here? Well, this is kind of tricky, so let's think through this. If w is always negative, then you're going to get when you insert a w, you're going to have this negative out front, and so this is going to turn into a positive. So minus w is always positive. So the absolute value of minus w, then we could just remove the absolute value and get this. But now we could bring that minus out front, and we're just left with 4w over w. Okay, these cancel, and we're just left with 4. So this limit is equal to 4. Okay, great. Now let's do the limit as x approaches 0 from the right. So in this case, since w is always positive, with the minus out front, you always have a negative number inside this absolute value. So to remove the absolute value, we need to do this, minus w. So this simplifies to minus 4w over w. So we're just left with minus 4. Okay, and so now, there you go. The limit as x approaches 0 from the left is 4. As x approaches 0 from the right is minus 4. So in general, this limit doesn't exist. And if we look at the graph, it's exactly what the graph shows. Yeah, so that's a really useful technique you want to keep in mind. If you're stuck analyzing a limit and you don't know what to do, then analyze the one-sided limits separately, because one-sided limits are going to be easier to deal with than two-sided limits. Okay, the limit as x approaches infinity of this rational function. So let's just divide the numerator and denominator by x. So we get, so 3 minus, and then 2. Okay, so as x goes to infinity, this goes to 0, so the numerator goes to 3. This goes to 0, the denominator goes to 2. 3 halves. So as x goes to infinity, we can see that the function approaches 3 halves. Okay, the limit as t approaches minus 7 of minus the square root of minus t plus 1. So let's plug in minus 7 and see what we get. So minus 7 is 7. Okay, so 4 times 2, you've got 2 root 2. There you go. This is continuous at minus 7. So when t is equal to minus 7, the function is continuous. Okay, the limit as x approaches 7 from the right of x plus the absolute value of 2x minus 14. All right, so in most circumstances, when we're dealing with an absolute value, we're going to need to analyze the problem to see if we can remove the absolute value. And, we can still do that here, but one thing about absolute values is any general absolute value expression is continuous everywhere. Yeah, so like all of the limits we've worked up to this point involving absolute values haven't been continuous at the crossover point where the expression inside the absolute value changed from positive to negative, because they were contained within a ratio. A ratio was involved. But just like a general expression where there's no ratio or something else involved, just a general absolute value expression is continuous everywhere, because absolute values, the characteristic of an absolute value is at the transition point where the expression inside the absolute value switches from positive to negative, you're going to have like a kink. The function's all of a sudden going to get to some point where the switch happens and it's just going to turn the other way and keep going. But it's going to be continuous. So we can just plug in 7 here. This might just be a continuous function. And so the direct substitution property applies. If you plug in 7 plus 2 times 7 is 14. So this is just 7. There you go. Absolute values are continuous everywhere. And that's exactly what we see. You've got the function at x is equal to 7. It has this non-smooth kink, but so what? That has nothing to do with continuity. So the function is just, it's a continuous function here. So that's what the limit is equal to. Now we could have analyzed this and said, okay, since 7 is, you always have x above 7, which means that 2x minus 14 is always positive. So we could have turned this into, you just remove the absolute value. And then you get 3x. 7 times 3 is 21, minus 14 is 7. Okay, the limit as w approaches minus 3 of minus 4. This is just the constant function, y is equal to minus 4. So any limit of this function, no matter what the input is, even if this was a limit at infinity, it is approaching minus 4. Right? There's y is equal to minus 4. It doesn't matter if this is a limit as w approaches a, no matter what a is, or if w is approaching plus or minus infinity. The limit is going to be always minus 4. But specifically in this case, at w is equal to minus 3, you can see how the function approaches minus 4. Okay, the limit as s approaches 9 of s minus 9 over the square root of s minus 3. And so there we go. We see this two-term expression with one of the terms being a root. So there's a high likelihood that the conjugate of this expression is going to be involved to solve this problem. So, okay, as s approaches 9, the numerator approaches 0, and the denominator also approaches 0. So we have a 0 over 0 indeterminate form. Let's manipulate this expression to put it into a different form, and we're going to do that by multiplying by 1 in the form of the conjugate of the denominator. So we've got, let's see, so in the numerator, multiplying these two terms, and then in the denominator you've got s minus 9. So the s minus 9s cancel, and you're left with, so now plugging in 9, you get square root of 9 is 3 plus 3 is 6. So this limit is equal to 6. We've taken this, put it into a different form, this form, so the graph of this equation is exactly the same as the graph of this equation, except there's a hole. Even though this is defined when s is equal to 9, this isn't. So you put a hole in this, or in this graph at s is equal to 9. So here's the graph of this function, and that's exactly what we see. There's a hole at s is equal to 9, and so the limit as s approaches 9 is just equal to what this function would be equal to if it was defined at s is equal to 9. Okay, the limit as h approaches 0 of 4 square root of 5 plus h minus 4 square root of 5 all over h. So, okay, we see another, here's a two-term expression with that involves these square roots. And even though both involve square roots, that's fine. So there's going to be a high likelihood that we're going to use the conjugate of this to solve the problem. So as h approaches 0, we get h is 0, so 4 root 5 minus 4 root 5. The numerator goes to 0. The denominator goes to 0. So there's a 0 over 0 indeterminate form. With these indeterminate forms, let's just try and remold the function to put it into a different form that's not indeterminate. We're going to do that by multiplying by 1 in the form of the conjugate of the numerator. So 4 and then plus 4 root 5. Okay, so what we're left with is, so you get 16 times 5 plus h. Then the middle term subtract out, and you just have 16 times 5. Okay, then you've got h times okay, so now let's see, let's do, so 16 times 5 plus x minus 16 times 5 is 16x. So 16h in the numerator so the h's cancel, and there we go. That's going to allow us to solve the limit. So you've got 4 plus. Okay, so as h approaches 0, plugging in 0, you get 4 root 5 plus 4 root 5 is 8 root 5. 1 over 8 root 5. So let's just rationalize this, and we get, so root 5 over 40. So this limit is equal to root 5 over 40. If we take a look at the graph, what we've got is, so this graph is just this graph, which is the domain of this graph. As long as h is greater than or equal to -5, this is defined, right? Because when h is less than -5, you can't have this negative under the square root. But anything, any h that's greater than or equal to -5, this is defined. However, since this is just this in a different form, then what this graph must be then is just this exact graph, but with a hole in it at h is equal to 0. And that's what we see, right? So this just cuts off when the input goes below -5, and then you have this hole at 0. And so the limit of this function as h approaches 0 is just what the function would be equal to if it was defined at 0, which is root 5 over 40. Or no, wait, this is 16. So this is 16 root 5 over 40. So 16 over 40 is 2/5. So 2 root 5 over 40, or 2 root 5 over 5. Okay, the limit as x approaches 1 of minus x minus 1 over x squared plus 2x minus 3. So the numerator goes to 0, and most likely the denominator goes to 0 as well. Let's see, if we factor the denominator, we get, so plus 3, x plus 3 times x minus 1. So yes, the denominator goes to 0 as well as x approaches 1. So, okay, but this simplifies to the x minus 1's cancel, and we get, Okay, so now plugging in 1 here, you get minus 1 over 4. Right, because this is just this graph with a hole in it at x is equal to 1. And so, therefore, this limit is just equal to what this function would be equal to if it was defined at that hole, which is minus 1/4. And there you go. So here's the graph of this function. There's the hole. So the limit as x approaches 1 is just this value, minus 1/4. Okay, the limit as s approaches 3 from the left of 3 over s minus 3. So the denominator goes to 0, and the numerator is non-zero. So this is going to be some sort of a vertical asymptote problem. And since we're doing a one-sided limit here, then this is going to be an infinite limit. So we've got, if s is approaching 3 from below 3, so you've got 2.9, 2.999, 2.9999. So anything below that's less than 3 minus 3 is going to be a negative value. So you have 3 divided by tiny, tiny negative numbers that are really close to 0. So you're going to get, the output's going to be a negative number that's getting larger and larger and larger in magnitude. So this is going to be equal to negative infinity. And that's what we see. So 3 is a vertical asymptote. And coming from the left, the function is going to negative infinity. Coming from the right, the function is going to positive infinity. So as s approaches 3 in general, this would be a d and e. Okay, the limit as w approaches infinity of minus 6 over w squared plus 2. This is a rational function, right? 6 is a polynomial, a degree 0 polynomial. So we have a limit at infinity of a rational function. Let's just divide the numerator and denominator by w to the power of the order of the denominator. So okay, we've got so 1 plus. Okay, now as w goes to infinity, this goes to 0. 2 over w squared goes to 0, so 1 plus 0 is 1. So you have a minus 0 over 1. This goes to 0. You have a horizontal asymptote at y is equal to 0. There you go. Okay, the limit as x approaches minus 2 of minus x minus 2 over the absolute value of minus x minus 2. So here we're approaching minus 2 from both sides in general, two-sided limit. And minus 2 is the crossover point where this expression switches from negative to positive inside of the absolute value. So what we're going to do is analyze the one-sided limits, each of the one-sided limits of this function. So x approaching 2 from the left, or minus 2 from the left. In that case, so if you had, let's see, minus 4 minus 2 is, so 4 minus 2. In that case, if x is anything less than minus 2, then this expression, this minus x minus 2 is always positive. So we can just remove the absolute value. Okay. So now these just cancel, and you're left with 1. So this is equal to 1. Now, approaching minus 2 from the right, then this minus x minus 2 is always negative, so we remove the absolute value but put a negative out front. So these cancel, and we're left with minus 1. So this is equal to minus 1. So there you go. This limit in general does not exist, because the limit as x approaches minus 2 from the left and from the right are two different limits. Okay, the limit as k approaches 2 of the absolute value of k minus 2 minus 3. Well, absolute values are in general continuous everywhere, unless you might have a function inside of the absolute value that isn't continuous everywhere, but an absolute value in general is continuous everywhere. So let's just plug in 2 and see what we get. So there you go. This is going to be equal to minus 3. Because where is there going to be a point of discontinuity in this function? The only way we could have a point of discontinuity is if we were dividing by 0 potentially, or if there was some function inside of the absolute value that wasn't defined at certain points. But here we've just got a k minus 2 inside of the absolute value, right? Because the absolute values, all they do is just, all an absolute value is doing is when the function inside of the absolute value changes signs, it just doesn't allow it to switch to negative. It just makes it stay positive. That's all it does, which is going to result in some sort of a non-smooth point, some sort of a kink, but not a point of discontinuity. And there you go. As k approaches 2, the function approaches this point of continuity at y is equal to minus 3. Okay, the limit as x approaches pi over 6 of 2 cosine of 2x. So maybe we could just plug this in, since cosine is continuous everywhere, and actually cosine has a domain of all real numbers. So yeah, we just plug this in. There's no vertical asymptotes or anything with cosine. Sine and cosine are continuous everywhere in their domains, like all of the other trig functions. However, unlike the other trig functions, sine and cosine have domains of all real numbers. So we just plug in pi over 6. So you have 2 cosine of pi over 3, 2 times cosine of pi over 3 is 1. So pi over 6 is, right around 0.5, so somewhere around here. It's each of the one-sided limits of this function. So x approaching 2 from the left, or minus 2 from the left. In that case, so if you had, let's see, minus 4 minus 2 is, so 4 minus 2. In that case, if x is anything less than minus 2, then this expression, this minus x minus 2, is always positive. So we can just remove the absolute value. Okay. So now these just cancel, and you're left with 1. So this is equal to 1. Now, approaching minus 2 from the right, then this minus x minus 2 is always negative, so we remove the absolute value but put a negative out front. So these cancel, and we're left with minus 1. So this is equal to minus 1. So there you go. This limit in general does not exist, because the limit as x approaches minus 2 from the left and from the right are two different limits. Okay, the limit as k approaches 2 of the absolute value of k minus 2 minus 3. Well, absolute values are in general continuous everywhere, unless you might have a function inside of the absolute value that isn't continuous everywhere, but an absolute value in general is continuous everywhere. So let's just plug in 2 and see what we get. So there you go. This is going to be equal to minus 3. Because where is there going to be a point of discontinuity in this function? The only way we could have a point of discontinuity is if we were dividing by 0 potentially, or if there was some function inside of the absolute value that wasn't defined at certain points. But here we've just got a k minus 2 inside of the absolute value, right? Because the absolute values, all they do is just, all an absolute value is doing is when the function inside of the absolute value changes signs, it just doesn't allow it to switch to negative. It just makes it stay positive. That's all it does, which is going to result in some sort of a non-smooth point, some sort of a kink, but not a point of discontinuity. And there you go. As k approaches 2, the function approaches this point of continuity at y is equal to minus 3. Okay, the limit as x approaches pi over 6 of 2 cosine of 2x. So maybe we could just plug this in, since cosine is continuous everywhere, and actually cosine has a domain of all real numbers. So yeah, we just plug this in. There's no vertical asymptotes or anything with cosine. Sine and cosine are continuous everywhere in their domains, like all of the other trig functions. However, unlike the other trig functions, sine and cosine have domains of all real numbers. So we just plug in pi over 6. So you have 2 cosine of pi over 3, 2 times cosine of pi over 3 is 1. So pi over 6 is, right around 0.5, so somewhere around here. Okay, the limit as r approaches infinity of 2r minus 2 over the square root of 2r squared plus 3. So we have a limit at infinity, and this is not a rational function, but it's similar. We've got a root, because this is not a polynomial down here, but we're still going to divide the numerator and denominator by r to the power, that's the order of the expression in the denominator. So we want to divide the numerator and denominator by r, okay? But in this case, once again, we're not going to have an issue because we're not going to negative infinity, but the idea is we divide the denominator by r, but in the form of the square root of r squared, which if r could be negative, then we would need to account for the fact that we don't want this in actuality, it would be equal to the absolute value of r. But since r is always positive, it doesn't matter. If r is positive, then we can just say that this is equal to r and not the absolute value of r. So, okay, then we've got dividing the numerator by r as well. So, okay. We've got, so 2r squared over r squared is, you have 2 plus, and then 2 minus, okay, so as r goes to infinity, the numerator approaches root 2, and the denominator approaches 2. So this limit goes to 2 over root 2. We can rationalize this and get 2 root 2 over 2. So y is equal to 2 root 2 over 2 is a horizontal asymptote of this function. There we go. Okay, limit as x approaches minus 1 of this rational function. So the denominator is going to 0, and most likely the numerator is as well, but maybe it's not. In that case, we would have a vertical asymptote problem. But let's see, factoring the numerator, we've got minus 3. So yeah, this is a 0 divided by 0 case, because the numerator goes to 0 and the denominator goes to 0. So we've got, let's see, the x plus 1s cancel, and you're left with x minus 3. So minus 1 minus 3 is minus 4. This is, the graph of this function is the line x minus 3 with a hole in it at minus 1 comma 4. There you go. As x approaches minus 1, the function approaches minus 4. Okay, the limit as x approaches infinity of 1 minus x squared over x cubed minus x minus 1. So we have a limit at infinity of a rational function, a ratio of polynomials. So let's divide the numerator and denominator by x to the power, that's the order of the denominator, so cubed. So you've got x cubed over x cubed, x over x cubed, okay. So let's see, 1 minus, and then, okay, so as x goes to infinity, the numerator goes to 0, and the denominator goes to 1. So this entire limit is equal to 0. There you go. As x approaches infinity, y is equal to 0. Okay, the limit as x approaches infinity of the square root of 1 plus 4x to the 6 over 2 minus x cubed. Let's divide the numerator and denominator by x cubed. But in this case, since x is going to infinity, we're not going to have to worry about the root. So let's see, we've got 1 plus 4x to the 6th, and then divided by the square root of x to the 6th, which in general, the square root of x to the 6th being x cubed would mean that you would need to put the absolute value here, right? Because you wouldn't want to say that the square root of minus 2 to the 6th is minus 2 cubed, which would be minus 8. That's not correct. But in this case, it doesn't matter because x is going to positive infinity. So if x is always positive, then you can't just state that this is x cubed. So we're dividing the numerator by x cubed and the denominator by x cubed. Okay. So 1, and then let's see, 1 over x to the 6th plus 4. Okay, as x goes to infinity, the numerator approaches the square root of 4, so it approaches 2, and the denominator approaches minus 1, so the entire limit approaches minus 2. So as x goes to infinity, the function approaches the line y is equal to minus 2. Okay, a limit at infinity of a rational function. Let's divide the numerator and denominator by x to the power, that's the order of the denominator, so x cubed. So you've got okay. So x minus 3 over x plus 1 over x squared, 1 minus... Okay, so as x goes to infinity, the denominator goes to 1, and the numerator, so all of this goes to 0, and you're just left with this x here. So we can say that this limit as x goes to infinity approaches x, which this is where slant asymptotes come from. As x gets bigger and bigger and bigger, the output of the function is getting closer and closer and closer to the line y is equal to x. However, what this still means, though, is that this is equal to infinity. Because the line y is equal to x, as x goes to infinity, the line y is equal to x just gets bigger and bigger and bigger. But still, when we look at the graph, what we see is, as x goes to infinity, it is the case that the function is getting closer and closer and closer to the line y is equal to x. Okay, the limit as x approaches infinity of the square root of x plus 3x squared over 4x minus 1. So let's just divide the numerator and denominator here. This is going to be an infinity over infinity indeterminate form. So let's, to remold this, to put it into a different form, let's divide the numerator and denominator by x to the order of the denominator, which is 1. Now we do have the root, but since x is approaching positive infinity, we don't have to worry about any, when we do this, we're going to divide by x in the form of the square root of x squared, but we don't have to worry about this being actually equal to the absolute value of x because x is always positive. So you've got, okay, so this is, now we've got 1 plus 3, and then 4 minus, okay. So as x goes to infinity, you've got the numerator goes to 1 and the denominator goes to 4. So this is equal to 1/4. And there we go. As x goes to infinity, the function approaches the horizontal line, y is equal to 1/4. The limit as k approaches 7 from the right of k minus 6 over k squared minus 14k plus 49. So plugging in 7, the numerator goes to 1. So this is probably going to be a vertical asymptote problem. Unless this doesn't go to 0, then this is just this function. This rational function is continuous at 7, but it's probably going to be a vertical asymptote problem. So factoring the denominator, we get 7 times 7. Yeah, so this is a vertical asymptote problem because you have a non-zero finite number being approached in the numerator and 0 being approached in the denominator. So, okay, approaching 7 from the right, k minus 7 is always above 0, is always positive. But actually with this k minus 7 squared, we could approach 7 in general, and we would be going to the same infinity on either side. But 7 from the right, you always got 7.01 minus 7, 7.0001 minus 7, 7.000 1,000 zeros 1 minus 7. So it's always some tiny positive number. You square that, you get a tiny positive number. Then this is approaching 1, so 1 divided by a tiny, tiny positive number is infinity. So this is an infinite limit that's equal to infinity. But you can see if this was 7 approaching 7 in general, then even though approaching 7 from below 7, you get k minus 7 is a negative number, tiny number. When you square it, you get a positive number anyway. And then here, it doesn't matter if k is approaching 7 from above or below. This is always approaching 1. Right? There you go. 7, k is equal to 7 is a vertical asymptote. And approaching 7 from the right, the function is going to infinity. Okay, the limit as x approaches negative infinity of the square root of 4x squared plus 3x plus 2x. So, okay, plugging in minus infinity, we've got minus infinity squared is positive infinity times 4 is positive infinity. 3 times negative infinity is negative infinity. Okay, and then 2 times negative infinity, you've got negative infinity. So, I mean, this is indeterminate. We don't know what this is here. So we don't know what the square root of this might be. And then now you're still subtracting infinity. So this is an indeterminate form. But we see we've got this 2-term expression here. One term is a square root term, and the other term is just a non-root term. So what we're going to do is we're going to multiply this by, we're going to use the conjugate of this to put this into a different form. So we'll multiply by 1 in the form of the conjugate of this. So okay. So you've got 4x squared plus 3x and then minus 4x squared. So you just have 3x in the numerator. Okay. So, but now we still have an indeterminate form. This is still going to be an infinity minus infinity. We'll have some sort of infinity in the numerator. So, but we've put this into a form that we can work with because we can divide the numerator and denominator by x to the order of the denominator, so x to the first. But now we've got x going to negative infinity, so we need to be careful because, so, okay. If we're going to divide this root term here by x, but we're going to put it in the form of the square root of x squared, well, now x is going to be negative, right? X is negative. So what we don't want to do is we don't want to be saying something like minus 5, the principal square root of minus 5 squared is minus 5, which is in essence what we would be doing if we just left it like this and brought the x squared inside of the root. So to account for this, we're going to put a negative here. And why does this work? Because all we're doing is this. All we're doing is, so the principal square root of x squared is the absolute value of x, right? In general. This accounts for the fact that you're not going to put minus 5 here. You'd put the absolute value of minus 5. And so now, but if you know that x is always negative, if you know x is going to be negative, then we can simplify this absolute value as just remove the absolute value and put a minus out front. So that's what we're doing here. We're just saying, okay, this is equal to the absolute value of x, right? But then we just take away the absolute value and put a minus out front. Okay, so 2x so we've got and so you've got 4 over x plus 3, the minus here, then minus 2. Okay, so now as x approaches negative infinity, 4 of x goes to 0, 3 plus 0 is 3. So what you've got is minus root 3 minus 2. Okay, and we can just do this. So 2 plus root 3. Now we can rationalize this final answer. So as x goes to negative infinity, the function is approaching 3 root 3 minus 6. The horizontal asymptote at y is equal to 3 root 3 minus 6. Okay, the limit as t approaches minus 2 of minus t plus 3. Well, polynomials like this line are continuous everywhere. So just plug in minus 2 for t. So minus 2, 2, and there you go. This is just a line. T is equal to minus 2. The function is approaching 5. Okay, the limit as w approaches minus 3 from the left of 2 times e to the 1 over w plus 3 over e to the 1 over w plus 3 plus 1. So, okay, as w approaches minus 3, these w plus 3s are going to 0. Now, but since we're approaching minus 3 from the left, then, so we can think about what is the limit as w approaches minus 3 from the left of 1 over w plus 3. So minus 3 from the left, you've got minus 3.0001, 3.000001, minus 3.1000 zeros 1. So you've always got a negative w whose magnitude is just a little bit greater than 3. So you're going to get a tinier and tinier, closer and closer to 0 negative number in the denominator. So then just 1 divided by this tiny negative number means that this is going to negative infinity. So what you've got here is 2e to the negative infinity over e to the negative infinity plus 1 is what this, we can think about what this is approaching as w approaches negative 3. And so now we know that e to the negative infinity is, you could take any exponent and bring the exponent into the denominator. And so e to the infinity is just infinity, right? E to 100 trillion is just another arbitrarily large number in magnitude. So this is approaching 0 and this is approaching 0. So the numerator is approaching 0 because 2 times 0 is 0. And the denominator is approaching 0 plus 1 is approaching 1. So this is approaching 0. And that's what we see as w approaches minus 3 from the left. The function is approaching, you have this jump discontinuity here, and the function is approaching 0. Okay, the limit as t approaches minus 1 of 2t minus 5. You just have a line here. Plug in the limit point every time. If you just have a polynomial and even just a simple line as the limit function, just plug in the limit point if it's a limit approaching a finite value. So there you go. You just have a line here that's continuous everywhere. So at minus 1, what is, you can't see it, but whatever the function is equal to, it's going to be minus 7. Okay, the limit as x approaches 0 from the right of 3x over x. So we can see we can cancel out those x's and get 3. Okay, so what exactly are we dealing with here? The limit as x approaches 0 from the right of 3 is just 3. And so, yeah, this is equal to 3. But what this is this function simplifies to the constant function y is equal to 3. So what that means is that this function is exactly the same as this function, the horizontal line at y is equal to 3, except there's a hole at 0 because you can't divide by 0, right? There you go. So, but what the limit is equal to as x approaches 0, well, just from the right, but it wouldn't matter. You could do a general limit here, but just from the right is what the function would be equal to if it was defined at 0, which is 3. Okay, the limit as r approaches 1 of f of r to where f of r is this piecewise function. So, okay, we've got it's defined to be 0 when r is less than 1, and then this minus r squared plus 2r when r is greater than or equal to 1. So at the transition point, what is the function doing? So we've got it's if this was defined when r was equal to 1, then it would be 0. If this was defined when, or it is defined when r is equal to 1, and so what this is equal to is you've got 2, so minus 1. So, okay, this then at r is equal to 1, you have a jump discontinuity, right? You've got r is equal to 1, then this function is equal to 0, so open circle here, and then when r is greater than or equal to 1, this is going to be, so you have a 1 here, you have closed circle, and this is a downward facing parabola, so something like this. So you have a jump discontinuity. So as r approaches 1 in general, the limit's not going to exist at a jump discontinuity. The limit as the input approaches a jump discontinuity in general always doesn't exist, right? Because the limit as r approaches 1 from the left and the limit as r approaches 1 from the right are not the same. The limit as r approaches infinity of r to the 5th minus 3r cubed plus r minus 2. So this is a polynomial, right? Now, if we plugged in infinity, we would get, so infinity to the 5th, then minus 3 times infinity is just infinity, then plus infinity, then minus 2. So, with this infinity minus infinity, all of this looks like you would say it's indeterminate, right? And in general, that is true. We would call this indeterminate, but we do know from algebra the end behavior of polynomials and how they work. In that, so when you're analyzing any polynomial as the input goes to positive or negative infinity, the leading term is going to always take over. You just ignore all the other terms except for the leading term and see what the leading term is doing. So in this case, you have a huge positive number to the 5th power is just going to be a huge positive number. So that's what as r goes to positive infinity, that's what the function's going to do. Because again, like the idea is when you plug in, if you plugged in 100,000, this is just going to dominate all of this. All of this taken together is going to be a tiny, at r is equal to 100,000, all of this taken together is going to be a tiny percentage of this. So there you go. As r goes to infinity, you can see we're not even at r is equal to 2 yet, and it's already starting to, r to the 5th is already starting to take over. Imagine as r goes to infinity. And it's the same idea as r goes to negative infinity. You just think about, okay, negative infinity to the 5th is negative infinity. So this is ballooning to negative infinity. Okay, the limit as x approaches negative infinity of x squared plus 2x to the 7th. So we have just another polynomial here. And so we just analyze what the leading term is doing. So minus infinity to the 7th is minus infinity times positive 2 is still minus infinity. So this must be, as x goes to negative infinity, this must be going to negative infinity. And there we go. Okay, the limit as r approaches 0 of 1/3 plus r cubed minus 1/27 over r. So we're going to get, this is going to approach 0 in the numerator and 0 in the denominator. So let's just go ahead and let's expand this out and see what happens. So, well, we do have a difference of 2 cubes. So perhaps factoring this would be useful. I guess let's try that first. So we know that a cubed minus b cubed is equal to a minus b, and then a squared plus ab plus b squared. Now here, in this case, we have a is equal to 1/3 plus r, and then b is equal to 1/3, positive 1/3, because we have a cubed minus b cubed. So, okay, what that results in is, so a minus b, 1/3 plus r minus 1/3 is just r. Okay, then you've got a squared, so let me do 1/3 plus r squared plus ab, so 1/9 plus r over 3, and then plus b squared. Okay, these r's cancel, and there we go. What we're left with is 1/3 plus r squared plus r over 3 plus 2/9. So as r approaches 0, you have 1/3 squared, 1/9 plus 2/9 is 3/9 is 1/3. And there we go. There's the function. This function here is just the same exact graph as this function, but with a hole in this graph at r is equal to 0. And so the limit as r approaches 0 is just what this function would be equal to at r is equal to 0, which is 1/3. The limit as x approaches negative infinity of the square root of 2x squared minus 5 all over x plus 1. Okay, so here this isn't a rational function, but we can still divide the numerator and denominator by x to the first, the order of the denominator. But now here we're going to need to be careful when dividing x by this square root, because now x is going to negative infinity. So okay, the denominator we divide by x, and the numerator we divide by x, but we're going to divide by x in the form of the square root of x squared. However, what we're going to do is, because we know x is negative, then we know that we're going to need to, this is equal to the absolute value of x, right? In general, for all x, the principal square root of x squared is equal to the absolute value of x. And so if x is positive, then we can just remove the absolute value and leave the x. That's how we simplify absolute values. But if x is negative, then if we know x is negative for sure, then we can simplify this by just removing the absolute values and putting a minus sign out front, right? And so what we're going to do here is just leave this leave the absolute value of x in this form, but then just put a minus sign out front. And so now we're just looking at the principal square root of x squared as without an absolute value. So we've got, so 1 plus, and then 2 minus 5 over x. Leave that minus sign out front. Okay, so now as x goes to negative infinity, this goes to 0, so the entire denominator goes to 1. 5 over x goes to 0, so you have 2 minus 0, and you're left with the square root of 2. So you've got just minus root 2. And so you can see how if we didn't make sure to add this negative sign here, then we'd have gotten positive root 2, right? And so yes, as x goes to positive infinity, this function approaches positive root 2. Y is equal to positive root 2, but not as x goes to negative infinity. As x goes to negative infinity, the function approaches the horizontal line, y is equal to negative root 2, square root of 2. The limit as x approaches 0 of sine of 3x over sine of 4x. Okay, so as x approaches 0, the numerator goes to 0, the denominator goes to 0. So let's try and manipulate this expression and put it into a different form. All right, so if we come to the trig identities, we've got a sum and difference formula for sine in that sine of alpha plus beta is equal to sine of alpha cosine of beta plus cosine of alpha sine of beta. So sine of A plus B is equal to sine of A cosine of B plus cosine of A sine of B. So what we can do is, let's go ahead and rewrite this limit as sine of 2x plus x over sine of 2x plus 2x. And so then what we get is, applying this trig identity, we get, so sine of 2x cosine of x plus cosine of 2x sine of x over sine of 2x cosine of 2x plus cosine of 2x sine of 2x. So that's going to be just 2 sine of 2x cosine of 2x. Okay, now let's divide the numerator and denominator by 2 sine of 2x cosine of 2x. So we get 1/2 sine of x over sine of 2x plus 1/2 cosine of x over cosine of 2x. All right. Now, next, let's apply the double angle formula for sine. Sine of 2 theta is equal to 2 sine theta cosine theta. So 2 times 2 sine x cosine x. Okay, now let's apply this double angle formula for cosine. And specifically, the 2 cosine of 2 theta is 2 cosine squared theta minus 1. So 2 times 2 cosine squared of x minus 1. Okay, so these sines cancel. And we're left with, so, okay, 1 over 4 cosine x. And then, let's see, 4 cosine squared x minus 2. All right. But now we can go ahead and let's input the limit point. So cosine of 0 is 1, so this goes to 1/4. Cosine squared of 0 is 1, so the denominator here goes to 4 minus 2, and the numerator, cosine of 0, is 1. So 1/4 plus 1/2 is 3/4. And that's the limit. Okay, so what we've done is we've remolded this function into this form, and even though this function doesn't exist at x is equal to 0, this function does. And so what we're finding when we input x is equal to 0, we're just finding that there's going to be a hole in this graph at x is equal to 0, since this isn't defined at x is equal to 0. But by inputting x is equal to 0 here, we're just finding what this function would be equal to if it was defined at that hole. So, right, as x approaches 0, there's a hole here, but what the function would be equal to if it was defined at the hole would be 3/4. So that's the limit. the limit as g approaches pi over 2 from the left of minus tangent of g. All right, so we can start by just inputting pi over 2 into this function here, because we know tangent is continuous everywhere in its domain. So maybe pi over 2 is within the domain. So minus tangent of pi over 2. So, okay, this is undefined. Now, so this is pi over 2 is not within the domain of this minus tangent, but we know that any point that's not within the domain of tangent is a vertical asymptote. Because, so, tangent is sine over cosine. And we know that sine and cosine have domain all real numbers. They're defined everywhere. And so the only reason tangent doesn't exist at some points is because it's when cosine is 0. But we also know that there's no point where both sine and cosine are 0 at the same time. So it's always, when tangent doesn't exist, you have cosine is approaching 0, and then sine is approaching some number that's not 0. So we know that this pi over 2, since this minus tangent of g isn't defined at this pi over 2, then this is going to be a vertical asymptote for sure. So now what we can do then is we can plug a number that's just below pi over 2, to the left of pi over 2, into this function and see if it's a large value in magnitude that's positive or negative. So we can do, let's take this and subtract. Okay, so we're just below pi over 2. So now let's take this and plug it into the function. And there you go. So this is going to negative infinity. And that's what we see. This is the vertical asymptote at pi over 2, and coming from the left, the function is going to negative infinity. What is the limit as x approaches 2 of the sine function of x cubed minus 7x plus 4? So here's another unconventional function, the sine function, but just like we talked about with the floor function, you should not be intimidated by this. Any type of function like this, the sine function, when you think about its graph, it's just going to have regions of continuity and potentially some regions of discontinuity. Okay, so the way the sine function works is if the input into the sine function is positive, then it's going to output 1, plus 1. If the input into the sine function is negative, then it's going to output negative 1. If the input into the sine function is 0, which is neither positive or negative, then the output of the sine function is going to be 0. So if you inputted 123, then the output of the sine function is 1. If you input minus 2, then the output is negative 1. If you input 0, then the output is 0. So the entire range of the sine function, no matter what the circumstance, is just plus 1, minus 1, or 0. It only has 3 possible outputs. All right, so what does the sine function of this third order polynomial mean? Well, okay, here's the graph. So again, the output is either minus 1 or plus 1, and these lines don't mean anything. It's just at these points there should be just a closed circle at 0. So if we overlay the polynomial onto the graph, so what we see is that when the polynomial is positive, the output of the entire function is plus 1. And when it's negative, in the negative region, the output is minus 1. But now, where the polynomial crosses the x-axis, so where it equals 0, then the sine function is also 0. So there should be open circles here and just a single closed circle at y is equal to 0. There shouldn't be any graph. These vertical lines shouldn't be there. Okay, so if we're taking the limit of a sine function like this, well, what you can see is that the majority of the input points into the function are going to be continuous. It's only where the function that's the argument of the sine function crosses the x-axis, or at least touches the x-axis, that you have a jump discontinuity in a sine function. Other than that, it's just a constant y is equal to minus 1 or y is equal to plus 1. So Let's plug in x is equal to 2 and see what we get. If the argument is not 0, then the function is continuous at that point. We just put the output of the sine function. So let's see, 2 cubed minus 7 times 2 plus 4, so minus 8 minus 4. There we go. The function is continuous at the limit point. This is just equal to, what is sine of minus 4? It's minus 1. Right, let's see, that's 1, 2, we're here. The function is continuous everywhere that there isn't a jump. The limit as x approaches minus 5 of h of x, where h of x is this piecewise defined function. So, okay, the limit point corresponds to the defining point of this piecewise function. So what we want to figure out is, what is this function, h of x, doing at x is equal to minus 5? Is it continuous? Is it a jump discontinuity? Is it a removable discontinuity? So we know that the function is defined at x is equal to minus 5 to be 5. The output is 5. H of minus 5 is 5. Okay, but all of h of x is such that everywhere where x is not equal to 5, h of x corresponds to this function. It's only when x is exactly equal to negative 5 that the output corresponds to y is equal to 5. And we know that the output of a limit, the evaluation of a limit, has absolutely nothing to do with what's occurring at the limit point itself. So we just really want to analyze what is the limit of this function as x approaches negative 5. We can effectively just ignore all of this because the limit function is defined to be this function everywhere for all inputs other than at the limit point, which, again, when we're evaluating limits, we don't care about what's occurring at the limit point. So, okay, we've got a rational function here. As x approaches minus 5, the numerator goes to 0, and the denominator, let's see, so x plus 5, the denominator goes to 0 as well, and you're going to have these x plus 5s cancel. So what we've got is, we have a hole here, right? This function here, the graph of this function is exactly the same as the graph of this function, except when x is equal to negative 5, there's a hole in the graph. So, I mean, we've already worked problems up to this point involving limits with holes, right? So what's the difference here? Well, the only difference is that the problems we've worked so far, the holes in the graphs were such that the entire function wasn't defined at the hole, because we were just taking like the limit of, and we were just dealing with a rational function like this. That's it. Here, the purpose of the piecewise function is just to say that, okay, at the hole, we're going to say that instead of the function being undefined, we're going to go ahead and define it, in this case to be 5. That's the only difference here. And so you might say, well, don't we need to check to see if what this function would be equal to if it was defined at the hole is equal to 5? Well, no, we don't. We don't care about whether or not 5 corresponds to what this function is equal to at the hole, if it was defined at the hole. We don't care. If it is 5, then okay, then the function is actually continuous at that point. If it's not 5, well, so what? It doesn't have any bearing on what the limit's going to be equal to. The limit is going to be equal to what the function would be equal to if it was defined at the hole, what this function would be equal to. So to figure that out, we just plug in minus 5 here. Minus 1/7, and that's the limit. Right, so there's the hole at x equal to minus 5, and there's what the function is defined to be at x is equal to minus 5. H of x, or h of minus 5, is positive 5, but it doesn't matter. The limit is just the y value at this hole, minus 1/7. The limit as s approaches 0 of cosine of pi over 2 minus s over s. All right, so plugging in 0, you've got the numerator goes to cosine of pi over 2, which is 0, and the denominator goes to 0, so you've got a 0 over 0 indeterminate form. So we want to try and remold this equation into a different form. If we take a look at the trig identities, we've got the co-function formulas, and cosine of pi over 2 minus theta is just equal to sine theta. So this limit is equal to cosine of pi over 2 minus s is just sine of s. So now we've got the limit as s approaches 0 of sine of s over s. And if you remember, this is a limit that the textbook evaluated with a whole geometric argument. They used geometry to prove this limit. And so the limit as x approaches 0 of sine of x over x, the textbook said it is equal to 1. So this limit is equal to 1. And so there's the graph of cosine of pi over 2 minus s over s. And as s approaches 0, the function approaches 1. The limit as t approaches 0 of t over tangent of 4t. So as t goes to 0, the numerator goes to 0, and tangent of 0 is 0. So we want to try and put this into a different form. We can start by changing tangent of 4t to sine of 4t over cosine of 4t. And so what we get is, let's see, t cosine of 4t over sine of 4t. All right, so next what we want to do is rewrite this as, so we've got, we can do t over sine of 4t times cosine of 4t. Okay, now let's apply the product rule. We know that we can, from the limit laws, we can write this as the limit as t approaches 0 of t over sine of 4t times the limit as t approaches 0 of cosine of 4t. Okay, so this limit is 1. Cosine of 0 is 1. Now here, we can notice is that this has a form that's similar to one of the limits that the textbook proved. The limit as x approaches 0 of, it was sine of x over x is equal to 1, which you could also state as the limit as x approaches 0 of x over sine of x is equal to 1. The limit as x approaches 0 of either this or its reciprocal work out to be equal to 1. The textbook used a whole geometric argument to prove this limit. And so we've got a similar form to this limit here, but it's not quite exactly what we need. So what we can do is we can multiply this by 1 in the form of 4 over 4. So I've just added a 4 in the numerator and the denominator, right? But then from here, we want to take 1/4 out of the limit. We can do that. And what we're left with is 4t over sine of 4t. And so now these forms match. If you just set 4t equal to x, then you have the limit as x approaches 0 of x over sine of x. So this is equal to 1. So we've got 1/4 times 1. This limit is equal to 1/4. If we take a look at the graph, so there's a hole when t is equal to 0 because you can't divide by 0, but as t approaches 0, the function approaches, this is 1/4. The limit as n approaches infinity of minus 3n sine of 1 over n. Okay, so plugging in infinity, 1 over n is going to 0. So the argument within the sine function is approaching 0. Since sine of 0 is 0, then sine of 1 over n is approaching 0. Now, minus 3 times infinity is minus infinity. So this entire limit is approaching minus infinity times 0. Now, like any kind of infinity times 0 is also an indeterminate form. And you might think, well, why wouldn't like an infinity times a 0 be equal to 0? Why would this be indeterminate? Well, because it depends on the rate at which this 0 is being approached and the rate at which this minus infinity is being approached. If for some n, for example, you have a minus infinity is, minus something times 10 to the 50th, let's say. So this huge negative number of order times 10 to the 50. But then for that same n, the 0 is something times 10 to the minus 15. So that's still really small. It's, 15 zeros and then some numbers. Well, 10 to the 50th times 10 to the 15th is something of order 10 to the 35th. That would still be an infinity, a negative infinity in this case. Or if for a certain value of n, this was like, a times 10 to the 15th, and this was a times 10 to the minus 14th or 15th, well, then this could potentially be approaching 0. So any kind of infinity times a 0 is an indeterminate form of a limit. So, okay, the only way we can solve this at the moment, any kind of indeterminate form, is to put the limit function into a new form that isn't indeterminate. We'll learn L'Hopital's rule in chapter 4, which is really helpful. But for now, how can we put this limit function into a different form? Well, what we can do is we can make a substitution. We could say, let's let x equal 1 over n. So we're going to substitute this 1 over n for x. We'll put a 1 over x here, but then we need to also replace the limit point as well. We need to replace the n approaching infinity with x approaching what? Well, to do that, we just say, as n approaches infinity, what does x approach? Well, we can see it's 0. So to make the substitution, then we've got the limit as x approaches 0 of, we're going to get minus 3 sine of x over x, because we have the 1 over x here for n. So we can take this minus 3 out of the limit. And what we're left with is the limit as x approaches 0 sine of x over x, which we talked about earlier, that this is a limit that the textbook proved using a geometric argument. This limit is equal to 1. So we're left with minus 3. This limit is equal to minus 3. If we take a look at the graph, as n approaches infinity, the function is approaching minus 3.